Good morning and welcome back to the lecture series in the matrix algebra. This is the second lecture. In the last lecture, we have observed that whenever you are giving any matrix A, then A plus A transpose is going to be a symmetric matrix. And I have given you the task that what happens with A minus A transpose. So I hope you all of may completed this task and reached to the conclusion. Conclusion should be in this form. First, let's see the conclusion by example. So let's say A be 1, 2, 3, 4, and then A transpose will be 1, 2, 3, 4. Now we are interested in A minus A transpose. So 1 minus 1, 0, 2 minus 3 minus 1, 3 minus 2, 1, 4 minus 4, 0. So it seems that it will be skew-symmetric matrix. So let's prove that. So I am posting as a theorem that let A be a square matrix then A minus A transpose is a skew-symmetric matrix. So again, to prove this, we will use the same fashion we have observed last time. So let's start with A, that A being Aij being n cross n matrix. So A transpose is Bij with the relation that Bij is nothing but Aj. Okay, now we do the C being A minus A transpose, but by C we mean Cij, and this is nothing but Aij minus Bij, that is Aij minus Bij. That is how we do the matrix subtraction. Means from this, what I mean, Cij is nothing but Aij minus Bij, but Bij is Aj, so Aij minus Aj. Okay, but what will be the A minus A transpose? That is nothing but the C transpose, correct? C transpose is, let's say, matrix T being Dij. Then what is the relation between Dij and Cij? So where Dij is nothing but Cji, correct? So let's just put entries here. So Cji is from this it is Aj minus Aij, correct? From this information, I and J I have just placed this way. So it is nothing but minus of Aij minus Aj. So can I write it is minus of Cij? Okay. So from these I conclude that D is nothing but minus of C. So C transpose is minus of C. But C is again a matrix A minus A transpose. So what I conclude? A minus A transpose is nothing but minus of A minus A transpose. here this is where, correct? Now, where this is object. So this says that A minus A transpose is a skew-symmetric matrix. Okay. So whenever you are given matrix A, for that you are having two things. One, that is A plus A transpose is a symmetric matrix, and A minus A transpose is a skew-symmetric matrix. Okay. One, from the original definition of the transpose, you may have observed that. Let me put here as a theorem. Right. For any matrix A transpose is nothing but A. So proof is very much obvious. And let A being Aij being M cross N matrix, then A transpose being B being Bij as N cross M matrix. What is the relation? Bij is nothing but Aj. Okay. So now we are interested in A transpose. That is the B transpose. Let's say it is C map. So what is the relation? Being Cij, C will be, it is M cross N matrix. What is the relation? Cij is nothing but Bji, but Bji is Aij. So the matrix Cij is nothing but the matrix Aij of the same order. But what is Cij? That is C being A transpose. This is nothing but A. So that concludes that A transpose is nothing but A. Okay. Now from this information and these two things together, what you conclude? If I consider this as two equations, let's say x plus y, and this is x minus y, being A, can I find out what is x and what is y? Yes. Similarly, we are going to do something here. I am having the information that A plus A transpose is a symmetric matrix and A minus A transpose is a skew-symmetric matrix. If I divide it by 2 and add up, what I will get? So what I mean by divide by 2, first of all? So first of all, by saying that I am dividing by 2, I am just multiplying scalar half, as I have explained previously, and adding up. So what will be the resulting matrix? The resulting matrix will be half of A plus half of A transpose plus half of A minus half of A transpose. But this will be cancelled with this due to the commutativity of the operations. So resultant matrix will be A. So any matrix, any square matrix can be written as sum of symmetric and skew-symmetric matrix. So that is what the next theorem is going to state. Any square matrix can be uniquely as sum of symmetric and skew-symmetric matrices. So exactly the same idea that I am going to use. So for the proof part, for a square matrix, A, we know that A plus A transpose, sorry, A plus A transpose is a symmetric matrix. So this also is a symmetric matrix, and A minus A transpose is a skew-symmetric matrix. So this, okay. So what now I conclude from this? Hence, A can be written as half of A plus A transpose plus half of A minus A transpose. So that says that I can write A as a sum of symmetric matrix and skew-symmetric matrix. But next question is, in the theorem, I have written something unique. So for the uniqueness part, we are going to do this. Um, for the uniqueness, let A being B plus C, where B is a symmetric matrix. Better we write B, and C be a skew-symmetric matrix. So what I have to conclude, that B must be that A plus A transpose by 2 and C must be A minus A transpose by 2. So how I can get it? So just only we know about the transpose. So we will perform the transpose operation. So what will be the A transpose? That is B plus C transpose. But that we know it can be seen as B transpose plus C transpose from the definition of the transpose. But what do we know about the symmetric B? It is a symmetric matrix, so it will be result to B. And what we know about the C, we know it is C transpose is minus. So what we are having, A transpose being B minus C, and we are having B plus C this. So from this information, we are going to get B. So how we get B? So let's say this is equation number 1 and this is equation number 2. So from 1 plus 2, what I get? This says that A plus A transpose is nothing but 2B. From this I conclude that B is half of A plus A transpose. And to get the C, what do we have to do? We do 1 minus 2. That is A minus A transpose. Result into 2C. So from that, I am having C being half of A minus A transpose. So this completes the uniqueness part. This uh, completes the proof. Right? Whenever we write a matrix A as a sum of symmetric and skew-symmetric matrices, this is the unique representation. Okay. Similarly, for the complex numbers, we know something like the conjugate. So, if matrix A is a complex matrix, then the A conjugate is nothing but the conjugate of each and every entry. Is the conjugate matrix of A. And it will be the same M cross N matrix, where A is M cross N matrix. Okay? And for the conjugate matrix also you can think of transpose, and that is called A, that is denoted as A star. A star is nothing but conjugate transpose. Of A. Okay, so let's see by example. Let's say A being 1 plus 2y, 3 minus I, 4 plus I, and 5 plus 6i. So what will be the A conjugate? A conjugate is 1 minus 2i, 3 plus I, 4 minus 4 minus I, and 5 minus 6i. Correct? And what will be the A star? The A star is nothing but A conjugate transpose. So all we have to do is the transpose of this. So 1 minus 2i, 4 minus I, 3 plus I, 5 minus 6i. Okay? So this is called conjugate transpose. So as we have result for transpose, we can think of for conjugate also. So for a matrix, if A is same as A transpose, conjugate transpose, then it is called Hermitian matrix. And if we are getting the negative for a matrix, if A is, let's say A star is minus A, then it is called Skew-Hermitian matrix. Okay? So if you are interested in the examples, how you see examples? See what is the objective. Start from that one, and you will get how we have to write elements. Okay. So start with any entry here. If I place 1, this is the conjugate transpose, so 1 will be there. But if I place I here, in the conjugate it will be minus I, and the transpose will not change the position. And I want these two entries same, so I cannot put any complex number here, correct? So similarly for the diagonal entry here, also I cannot place the complex entry because it is not going to change position. But if I place 3 plus 3 here, first of all, then the conjugate will be 3 here and the transpose will place 3 here. If I plus put for I, then in the conjugate it will be minus 4i and it will come here. Okay. So how I have to put the entry here? It must be 3 minus 4i. And here it will be automatically 3 plus 4i. Correct? So real number must be in the symmetric matrix way, but the complex number must be in the skew symmetric matrix way. That we have seen. Okay, so wherever I am placing 4, I have to place minus 4 with I, and real numbers must be the same. Similarly, for the skew symmetric matrices, if you are interested in the example, what I have to do, see if I place here 1, then in the A star it will be conjugate. So my 1 here and its transpose will place here, but I want minus it. So I cannot place 1 here. Okay, so I can have to place 0. But if I want to place I here, then it will be minus I here, correct? And in the transpose, it will not change the position, so it will remain there. So now I want A star being minus A, so that this will work. Okay. Now if I place 2 here, then in the conjugate it will remain 2 here, but its transpose will come here. Then I want a minus sign, so here I have to place minus 2, correct? And here it must be minus 2. If I place 3i here, then in the conjugate it will be minus 3i, and for the transpose it will come here. So the entry, how it uh, here, first of all I want minus 3i, okay, but it is appearing here, so this entry must be plus 3i, then only this appear as minus, correct? So here minus 3i. Similarly, here if I place 1, then it will not work. Means any real number will not work. So 0 must be there for real part. And for the imaginary part, what I have to do, I have to place any number. I can place any number. Okay? So let me say 5i. So it will be minus 5i. So this will work perfectly good. So this is how we can construct examples of symmetric and skew-symmetric matrices. You know something like matrix multiplication, and just placing one example, you are having information. Let's say 1, 2, 3, 4. This is matrix A, and the B matrix 5, 6, 7, 8. Then how you do a matrix multiplication? 1 multiplied with 5 plus 2 multiplied with 7. That will be the resultant matrix A multiplied with B. And for this, 2 multiplied with 6 plus, 1 multiplied with 6 plus 2 multiplied with 8. Similarly here, for 3 multiplied with 5 plus 4 multiplied with 7. And for here, 3 multiplied with 6 and 4 multiplied with 8. That is how you used to do matrix multiplication. This entry multiplied with these entries and corresponding sum. So try to define, I am giving you as a task, give general definition of matrix multiplication. Okay? So we will meet in the next session. Thank you.